Hello, my name is Alex Joannis, and I'm a fourth-year chemistry major. In this video, I'll be walking you through question 1 from chapter 7.3 of the General Chemistry Workbook. Here's the question we'll be looking at. What, if anything, is wrong with each of the following Lewis structures drawn below? We're given 5 molecular formulas, along with 5 matching Lewis structures. Our job is going to be looking at each of these structures that they've made and determining exactly what problems each of them might have. So, in order to answer any of these questions, you've got to understand the octet rule. Now, the octet rule tells us that main group elements, that is, elements that belong here, not transition metals, these main group elements generally bond in a way that gives them 8 valence electrons. The obvious exception to this rule being hydrogen, which only bonds in ways that give it 2 valence electrons. Let's illustrate the octet rule with a molecule of water, or H2O. We know that oxygen is a group 16 element, we can see that on the periodic table here, so we know that based on that placement on the periodic table, it natively has 6 valence electrons. Now, Hund's rule tells us to properly draw the Lewis dot structure for this element, we need to first fill in electrons one at a time around the 4 sides of the element's symbol. Then, we've got 2 electrons left over that will be paired up to form lone pairs. And as we can see, we've got 2 lone pairs on a single oxygen atom. This is an oxygen atom. We've got 2 lone pairs that will not be involved in bonding, and 2 unpaired electrons that will be used to form bonds. We'll use open circles to express unpaired electrons, and closed circles to express electrons trapped in lone pairs. So let me rewrite our oxygen atom using this new notation. So to reiterate, our closed circles are electrons tied down in lone pairs that will not be available for bonding, and our open circles will be electrons that are available for bonding. So open circles are here, and closed circles, our lone pairs, are here. Now, hydrogen's got a lot simpler of a Lewis structure. As we can see, it's right here on the periodic table. It's in row 1, and it only has 1 valence electron. So we'll draw an open circle here, and this is the Lewis structure for a hydrogen atom. I think it's important to note that we've only got 1 electron available for bonding, and we have 0 lone pairs anywhere on this atom. So hydrogen has 0 lone pairs, and will only form 1 bond. Now, back to the octet rule. We know that oxygen, like almost every other element, needs 8 valence electrons to be stable and obviously to satisfy the octet rule. Hydrogen is the exception. It'll only have 2 valence electrons when it bonds properly. Now, our oxygen already has 6 electrons, and it only needs 2 more to have an octet. If we count up the number of unpaired electrons we have available from hydrogens that we need to use to form H2O, we notice that we have 1 unpaired electron and 2 unpaired electrons. We might notice that we can form a single bond with oxygen and one of the hydrogens, and then form another single bond with oxygen and the other hydrogen. And I'll just rewrite this Lewis structure a little bit more neatly right here. And this is the Lewis structure that we just drew for water. So now we should evaluate the correctness of our Lewis structure. First, we need to see if the total number of electrons shown equals the sum of the valence electrons in each of our starting atoms. Now, oxygen had 6 electrons to contribute, and each hydrogen only had 1 electron to contribute. So the sum of our constituent elements' electrons is 8. Are there no more or no less than 8 electrons shown in our Lewis structure? Well, let's count. We've got 4 from lone pairs and 4 in bonds, because remember, each single bond contains 2 electrons. So we've got 4 and 4, that gives us our total of 8. So there are a total of 8 electrons in the structure we drew, which agrees with the amount of electrons we know we should have from counting up the electrons contributed by each of the different elements. So we've satisfied the first condition for a valid Lewis structure. The other condition you should check is that each element, except for hydrogen, has an octet. In our structure, each hydrogen is only involved in one single bond, so there's nothing to worry about with them. If the hydrogen, for example, was involved in a double bond, or in more than one single bond, which we know isn't possible because it only has one electron for bonding, then we would have a problem. So what about our oxygen? Well, we can count the electrons that are around that. Again, we've got 2 trapped up in this lone pair and 2 trapped up in the other lone pair. So we've got 4 from lone pairs, and we've got 2 in this single bond and 2 in this single bond. So again, we have a total of 8 electrons around oxygen, which satisfies the octet rule that says that every element that is in hydrogen should have 8 electrons around it. So oxygen satisfies the octet rule in our Lewis structure. So now let's finally take a look at part A of this question and see if the structure that they drew for ammonia fits our 2 rules. That we have the correct number of valence electrons for the entire Lewis structure, and also that we have the correct number of valence electrons around each individual atom, whether that be only 2 valence electrons for each of our hydrogens or a full octet when it comes to any other atoms we might have in our structure. I would suggest we begin by drawing the Lewis structure for each of these 2 elements in ammonia, those elements being hydrogen and nitrogen. Pause the video now and attempt to draw the structures on your own. Resume the video when you feel confident in your answer. This is what your Lewis structure should look like. Now, let's count up the valence electrons contributed by each element. There are 5 being contributed by the single nitrogen, and 1 is being contributed by each of the 3 hydrogens. This means we have a total of 8 valence electrons to work with. Count up the valence electrons shown in figure A. Does the figure have 8 valence electrons like we've discovered it should? Pause the video now and resume when you've come to an answer. You should have found that this is not, in fact, a good Lewis structure. There aren't enough electrons shown here, and if you're unsure of where these missing electrons belong, I'd suggest checking our second condition. If we check each element for the appropriate number of electrons in lone pairs, we'll find out where to put the missing electrons. Pause the video and attempt to solve the problem now. You should have noted that nitrogen doesn't have the right number of electrons around it. As it's drawn, it only has 6. It's also missing the lone pairs of electrons that we normally draw in its Lewis structure. To fix this figure, all we need to do is place a lone pair of electrons on the nitrogen, and you can use our 2 rules to check that we have a correct structure. Based on our solution to part A, we can actually come up with a third rule that we can use to determine the validity of a Lewis structure. And that third rule will be that each element in that Lewis structure has the correct number of lone pairs. We were able to solve problem A simply by putting the correct number of lone pairs on nitrogen. How do we tell how many lone pairs any element should have? Well, for that, we take a look at the Lewis structure. The Lewis structure for nitrogen, as we drew, has a single lone pair. So whenever you see nitrogen in a Lewis structure for a molecule, it too should have a single lone pair. At this point, I'd like to encourage you to use everything you've learned thus far to solve parts B through E on your own. Pause the video here, and when we resume, I'll review the problems with each structure and how to fix them. Feel free to rewind the video to review the criteria for good Lewis structures. So, here are the answers that you should have gotten. Let's run through what each of the problems were with the Lewis structures and what we did to fix them. B was incorrect because hydrogen is involved in double bonds as shown, despite only having 1 electron to bond with. The entire structure also has 2 more electrons than it should. To fix this, we removed both double bonds and drew a new double bond between the 2 carbons. Now we have the correct number of total valence electrons, and everything has its octet. Except for hydrogen, of course, which now is involved only in 1 single bond. C was incorrect for a few reasons too. Not only do we have 10 valence electrons around carbon, we also only have 2 valence electrons around oxygen. We can fix this structure by drawing the correct number of lone pairs on oxygen and moving one of the hydrogens from carbon to oxygen. Now, every element has its octet, and we have the correct number of total electrons. D also shows 2 fewer electrons than there should be. Each oxygen contributes 6, and carbon contributes 4, so we should see a total of 16. But all that's shown with the bonds that are drawn are 4. We could fix this structure by filling in the missing electrons, as shown. Now, what exactly is wrong with E? It doesn't really seem like there's much wrong with the structure that they gave us, but the key lies with this oxygen right here. While it's true that the total valence electrons around this structure is exactly as it should be, and that this oxygen does have its octet, but if we remember what the Lewis structure looks like for oxygen, like we drew earlier, we should have 2 lone pairs, and only 2 electrons that are unpaired and available for either a double bond or 2 single bonds. Now, if we look back at the oxygen that we have drawn, or that they drew in their Lewis structure, it's only got 1 lone pair, and it is involved in a total of 3 bonds, a double bond and a single bond. This oxygen is what makes that Lewis structure incorrect. We also need to make sure, whenever we draw a Lewis structure, that we have the correct number of lone pairs on each of our atoms. I've only drawn 2 possible solutions, but there are many more valid structures. The key is to make sure that, first, you have the correct number of total electrons, and then that each element has its octet, and that hydrogen is only involved in 1 single bond. The final thing to check is that each element has the correct usual number of lone pairs. That is to say, carbon, for example, if we were to draw the Lewis structure for a carbon atom, that carbon has 0 lone pairs. And that oxygen, as we've drawn already and will draw again, should have 2 lone pairs.